understood before we can.
Natalie, have you? Is it clear?
It's kind of for you. Oh, the kids have come. Get out.
She's not responding.
Okay.
Would first inquire if we are moving at the same pace with her.
A little. Okay. Maybe we need somebody who can what? She speaks French.
Yeah, she speaks French.
So anybody who knows French who can explain to her?
Providence.
Mariam, you can speak some French to her.
Okay, maybe you'll get time and then we see. Okay, but everybody else? Okay. So we still have 3 other models. So model number 1. So we can start with what called a null model. So this is a model which assumes that milk yield is not affected by treatment, is not affected by the cow, is not affected by the milkman. So in this case, you ignore the effect of the feed, you ignore the effect of the cow, you also ignore the effect of the milkman. And so in this case, you just have the general population. So we assume that all the milk that are produced comes from one uniform population, and then any variation that we observe between them is supposed to be our experimental error. In the second model, we can ignore the effect of the cow and the effect of the milkman. So in this case, we remove the blocking factors. We assume that milk yield will only depend on the effect of the feed and anything else. So what is included here in the error? What do we have in the error term?
Experimental error.
What will be the composition of the experimental error?
It could be maybe
treatment error.
value, maybe spilling some of the milk.
So in this case, any effect of the cow will also be taken as an experimental error. Any effect of milkman will also be taken as experimental error. Okay? So for model 1 and model 2, which one has the biggest error?
Model 1.
Model 2.
Why is model 1 having the biggest error?
I say model 2 has the biggest error.
You defend your answer.
I think model 1 because it has
The effect of the feed. I think
and it
model
has so many blocking factors.
Okay. So in model 1,
It's both treatment and experimental error.
yeah, so in model 1, we also have the effect of the effect of the treatment because we ignore it. We have the effect of the milkman and we have the effect of the cow. The cow, the milkman, and then the errors, the feed. So all of them will be here. So this will be much bigger than here because here we have removed the effect of the feed from the error. What is remaining now is the effect of the cow and the effect of the milkman. Is that clear?
Yes.
Yeah.
Okay. Now when we go to model 3 and 4, a model with a randomized complete block design, but are using one blocking factor at a time. So with the model 3, we ignore the effect of the milkman. So here you have the effect of the feed plus the effect of the cow. So the error term here will have the effect of the milkman.
Milkman.
Okay? And then with the RCBD, with the milkman as a blocking factor, that means we ignore the effect of the cow. And so here we have the effect of the feed, the effect of the milkman, and the error. So the error here will have the effect of the cow. And then for the full model, you remove the milkman, you remove the effect of the cow, you remove the effect of the feed. What remains here is what is error. So compared to, if we look at 3 and 4, which one do you think has the smaller error?
It is 5.
No, I'm saying 3 and 4.
3 has the
It's 4.
Okay, somebody said 3, somebody said 4. Those who say 3, why 3?
For 3, we realize that
The
the
milkman
milkman
effect
And
is
the
very
effect.
on the milk production compared to the other factors.
I think the variation of the milkman is very low, except for the outlier of milkman 5.
Okay.
Doctor,
Yes, it's the same.
yeah, I think it's
I think it's the
3
same.
because
3 with less error.
the feeds directly affect the milk.
Both 3 and 4, their treatment, the feed is taken away from the error, no? In 3, the error has the milkman effect, no? And in 4, the error has the cow effect.
Yeah.
No, in 3
so
the error has the cow effect.
So which one, 3 or 4, which one has a bigger error?
4
4
has
has
the
the
big
4 has the bigger
Biggest
one.
error.
because the cow feed has
4 has the
the
biggest
3
error.
has
Okay, so
production.
if we come back here, you see, if we come back here, we seems to have a lot more variation between the cows. So if we remove it from the model, we remove it from the error, that means it's going to remove a lot. So that means it is this one which is is a smaller variability. So when we look here, you find that in model 3, we remove the effect of the cow, which is larger. So the milkman effect is in the error, and we expect this error to be smaller than this particular error. Okay? Is that clear
Yes.
to everybody?
Yes.
Yes.
Okay. So now what we are going to do now is we are going now to look at each of the model one by one and look at the error term, and then we are going to compare the different error terms there. Okay, so here the first thing that we do is we are going to look at the null model. So remember, the null model, we are ignoring the effect of the feed, we are ignoring the effect of the cow, we are ignoring the effect of the milkman. Okay. So in this case, we indicated that that this one will have the highest amount of error because all the other effect will be in the error. So in this case here, if we do the analysis of variance, so we say all effects are in the error term, and the error term in this case, if you look at the mean sums of squares for error, the error term here is 12.36. Okay. So for our model 1, which is we have the general mean and the error term, and our error term in this case is our 12.36. Is that clear to everybody?
Yes, it is.
Yeah.
Okay.
Yes, Doctor.
Now,
Doctor, how did we arrive to 12?
No, that one we are going to run the analysis on the computer, and then the computer will give us the. This is done. This is the computer generates the analysis from the. That's the model. Okay. So for now, we will see how to generate this. Okay. So can we proceed to model number 2?
Yes.
Yes, doctor.
So with model number 2, when we ignore the cow and the milkman effect, so you can see in our model now we have the feed, and then we have the residue. The residue is anything else that remains. So now let's compare the error in model 1 and model 2. You can see that model 1 has bigger error compared to model number 2. Okay?
Yes.
We're going to come and look at the other things later on. Okay, so here you have 12.361 versus 7.036. Now let's look at model number 3. So model number 2 is the one that has the feed, and model number 3 is the one with the feed and the cow effect. And we said this should be the model with the smallest. We agreed that this would be the model with the smallest error, the smallest error, because we remove the cow effect and the feed effect from the data. Whatever remain is the milkman effect and any other thing. So from here you can see that there is a big difference between model number 2 and model number 3. So actually we have almost reduced, we have cut our error by almost half by bringing in the cow in the model, the cow effect. Okay. Now let's go to our model number 4. So model number 4 has feed and the milkman, and we had agreed that this model should actually be the between model 3 and 4. We agreed that model 4 should be the one with the IS, and you can see from here that model 4 is actually 7.76, and it looks like model 4 perform even worse than model number 2. Do you see?
Yes.
What could be explanation here?
It had number 4 probably had a bigger outlier.
But the outlier has not gone away from
Maybe,
the data.
Doctor, may I try?
Yes.
Maybe blocking with the milkman wasn't necessary.
Okay. So
think-
blocking with the, yeah, so what we're saying that blocking with the, actually the blocks are not, the milkmen are not different from each other. So if you block from the milkman, you don't gain very much. Now this is related to what we call when you're calculating the variance. How do we calculate the variance? We have what we call the degrees of freedom at the bottom. I'm going to explain this later at some point in time. Okay, so we can see from here that although blocking is important, if you don't block well, you may actually perform worse than if somebody who did not block. And this is the case that we have in this particular analysis. So now let's go and look at model number 5. So model number 5 has the feed, as the cow, as the milkman. Okay? And then as our residue, that is 3.067. So now let's look here now. We can compare. We have our model 1, which is the null model with the IS noise. And then we have our model 2, which is a similar noise with model number 4, and then we have model number 3 and number 5 with similar error. So now we have models that are competing in this time. So which one are we going to end up with now? Remember, we want to have the smallest error possible.
We shall end up with model 5 and 3.
Model.
So if you are now to choose between model 5 and model 3, which one would you
It
choose?
is 5 automatically. 5.
Model.
Because it has the smallest noise.
No, yes.
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 Okay, you first
definitely.
discuss. Give me 1 minute. You discuss, and then I will come back.
Mm-hmm. Maria,
What are we discussing?
why are you
Which of the models would you choose?
why are you taking 5 and why are you choosing 3? But the answer is okay. We are looking at the error. The values are clear. There any other thing to discuss about?
It could be.
Like what?
So
What could be the reason why you are choosing model 5 other than
Class,
model 3?
class me, I would choose model of 3 because now adding in the milkmen, it will cost us a lot, yet the milkmen are not even contributing much to the variance. So it will cost you much or more experimental material when you're using model 5. Yet the variance or the contribution of the milkmen is not that important.
So does it mean you are ignoring the issue of choosing one with the smallest error?
I think the difference in the error may not be as significant as the cost of using both blocking. So that's why model 3 may be more desirable because the difference between 3.335 and 3.067 is quite small. So rather than incur the cost of doing the blocking with a milkman, you'd rather go with model 3.
Excuse me, about the cost. I thought we are doing this after we have like collected the data. So it's just when you come to in my opinion, it's when you come to the data analysis. So there's no really cost there. You have your data and you're going to choose how you're going to analyze them.
Okay, if that's the case, then you take the lowest variance.
Because
if the experiment is already done, then you'd go with the lowest. If it's before, then the third is best. Model 3 is best.
Like,
I think you plan for the
in the
yeah.
first place, you are not yet aware that maybe I'm going to get such results. So here you got your results after even putting in your cost and you are analyzing just. So I think Albert could be right.
Maybe
Yeah,
an
I agree
inquiry.
with that.
An
Yes.
inquiry. In terms of recommendation for the best model, I think we'd look at the issue of costs and we will go with the model 3 because there we have realized that milkmen have no significant effect on the milk yield. So would consider model 3 other than model 5. But if we are looking at which one produces the best results, then model 5 would work. But in terms of the economy, model 3 would work. And that's my say about it.
Yeah, I agree with you.
I agree with that.
It's okay.
Maybe we would want to know at what stage do we choose the models when he comes back.
Yeah, that's an important thing to know.
Yes.
Okay.
An inquiry, is our friend on? Natalie.
Providence.
What of me? Even me, I'm on.
Fazil. Providence, are you there?
Yes, I'm here.
But
what Nathan wants to know, I didn't understand his question.
You didn't understand his question?
He can talk to me in French.
Mariam, you can help us with French here.
Providence, bonjour, bonsoir.
You told me you know French. Maybe Albert can
If Natalie is there.
Apart from I don't have any other.
Well,
I can follow up, but slowly in English.
Can Natalie, I want to listen to Natalie. I can explain her if I need.
Oh, yeah.
People about the question on when to apply the design. I think you use the design before collecting the data because it is experimental design. You're designing how to do the experiment.
And then it guides you on how many treatments you need to apply.
Yes.
Then Teddy, maybe you to inquire. How do you do prior to the experiment or prior to your data collection? If you're because here we are getting the results that we are using.
These are results from the experiment, but the RCBD and the CRD and the Latin square are experimental designs. They help you to design how to do the experiment before you collect the data.
So are they like in form of simulations? You first simulate before the actual.
I don't know about that, but
they are part of the methodology. By the time you go to carry out the experiment, you've already
designed your experiment.
understood
Yes.
how you have the design, how you're going to carry out the results, how you plan to analyze them.
The experimental designs.
Because if you're applying many treatment factors, then it will definitely guide you on which design you're going to. If you're applying many treatments, same thing.
Now, what if through the literature review you have realized that the milkman had no effect in some other designs? Now, won't you apply that and then you choose the one which could help you save on resources?
Exactly. I think that's what they are saying. Yeah. The question I think was like for learning purposes, but in my opinion, it does not work like this. You don't look at the data at the end, but what Teddy has said that you consider how your data will come out at the start of the experiment. Maybe through your literature review, you have known that the milkmen have no effect, so you'll just go straight to which one? To 3. You won't have to consider 5 as you design your experiments to be RCBD instead of Latin square, something like that. But I think Doctor wanted us to work on something as he's away. Maybe that's what I think.
Still, I'm getting confused more. If you can say we tested the models.
In the beginning, I had understood also, but anyway, we shall maybe inquire and clarify.
What had you understood?
Because for me, I thought when we discussed about the issue of cost and recommendation, maybe someone asked maybe recommend, but then when Ted said that you choose your model even before you collect the data, that is where I need clarification. Do we assimilate and know that maybe this one will work best? Maybe depending on your data or what?
And then the variance, which means we have to have results.
Because
for
in
us
all
to
this,
analyze the variance.
in all this, yes.
I think in my opinion, as you are starting your experiment, most of the things that you're just anticipating.
Yes.
Because these animals, you might take assumption that they are different, when actually they are not different. So you can only see that after doing the experiment.
And in order to come up with these errors, you must have had results.
Yes.
On the question of when do you choose the model, of course you have to choose the model before you start the experiment.
Yes, that's what I'm also thinking, because Tom, I think from the start, you're deciding, by the time you're leaving out the milkman, that means the design has already changed. You're not blocked. If you choose not to block in your experiment, then I don't expect you to go and do RBCD.
I'd like to clarify something. when you were studying the designs, like when you went to RCBD, doctor told us that you have to know your experimental units. So before you do the blocking, you have to know that there is variation in the cows. Or there is no variation in the milkman.
Before? Are you talking of before?
Like when he was explaining to us the designs, when we came to the RCBD, he told us that you have to know your experimental units.
Yes, what Ted is saying is true.
Like, so before you choose what to use for blocking, you have to know your experimental units.
I agree with you, Ted, but there is a possibility of assuming that maybe my cows are the same, but at the end of the experiment, you find out that they are not.
Emmanuel.
Yes, please.
I think that is not
This data we are seeing right now, it is just for purposes of study, I think. It's like someone got data and chose to do analysis using all the models to see how the data
Thank you. It is just an example to help us understand.
Yes.
Okay.
And actually from the results, you can see that model 5 would give you the best results, the most accurate, because it has the lowest.
My question. Question.
Yes, please.
But is that necessary?
Why is model 4 having the highest error?
Model 4.
You see, model 4 is looking at effect of, is not including all the blocking factors. Let's say you ignore the effect of cow.
No, model 4 would have ignored the milkman.
Look at the milkman.
Model 4 would have only ignored the milkman, so meaning all the others still hold.
I thought milkman is there. I think milkman is involved in block 4. That is why the error is high.
They've ignored.
Yes, because the variance is very small.
No, in model 4, they
Members.
ignored the cow.
Excuse me. Members.
Yes.
Hello?
Yes, please.
Hello.
Yes, I believe that is not for example purposes or something. It is from publications, and that is what a thorough literature search does. Whatever you're going to try and do has already been done by somebody to some extent, and you're just modifying something small so that you add to what has already been done. So that data was obtained from publications and is definitely right.
No, my question
What
is
I
true.
think is this. What I think is this. This data was given to us to help us understand which is the best model one can use for their experiments. I don't know about Joseph's idea, but I am thinking this data was given to us to evaluate which is the best model to use.
Exactly.
That's why he asked at the end, which one do you think is the best model? That's why it was his last question.
I agree. Barbara.
Yes.
Someone asked the question that from the data we are having, why is it that model 4 has the, was someone asking like model 4 has the highest?
Has higher
I
data
was asking
than
that.
model
I was asking that.
variance. We have two models. We have model 1 and model 4. So model 4 has the second highest error. So
Model 4 has the highest error. If you
The
look at the
second
values.
highest.
I think that's the highest
Okay,
because
the second highest.
The other treatment factor you considered had a very minimal variable.
Exactly.
compared
So
to
when you look at
five
model 4,
three.
they ignored the cow effect and instead included milkman effect. But we saw from the previous observation that there was more variation with cow effect compared to milkman effect. That's why you have a bigger error, I think.
But
That's
how
what I'm
come model 4 has a higher error than model 2?
What they are
One
trying to
of
ask,
our students.
Mbazira, what they are trying to ask is this. Why is it that when the milkman is used as a block, help them understand the knowledge under that. When it is used as a block, there is a bigger error compared to when the cow is used, cow effect is used in the model.
What we're trying to say is that the milkman effect was not necessary in the experiment, while on the other hand, 2 is high because you instead included the milkman effect and left out the cow effect, which was more important than the milkman effect.
Meaning in brief,
So
there
the
is more
noise
variability.
is louder in the results of 2 because the other big effect, which is the cow effect, was ignored. Hence the bigger error.
Exactly. So it's like we are taking assumption.
No, but
no effect that you're taking. When you ignore the cow effect and include milkman effect, it's like you're saying the milk yield is not affected much by the difference in the cows. Yet
Okay. Okay, thank you very much for the very nice discussion that has been going on. I think a number we have got the thing. I see the knowledge coming. Okay, just a clarification, a few things. So the first thing here is, as has been pointed out, this data here is used for illustration. The actual design for this experiment was a Latin square design. So you always design, you first choose a design. After taking a design, you go and do your experiment and collect your data. After collecting the data, now you come and do the analysis. Now, of course, sometimes you may make a wrong assumption. Like in this case, for example, the person assumed that there will be the effect of the cow, there will be the effect of the milkman. But then when we do the analysis, we realize that the milkman effect actually is very minimum. So what this means is that next time you're going to do a similar experiment, you may not have to worry about the milkman. You can only block using the cow. So there may be no need of having a Latin square design, since the effect of the milkman is actually very low. So you can see from here that if you look at model number 3 and model number 5, model number 5 is a big model compared to model number 3. But the difference between model, in terms of the residue, the error, the difference between model 3 and model 5 is actually rather small. So there is what we call parsimony in statistics. If you have two models that are competing with each other, then the best model would be the one that is simpler than. So in this case, which model 3 and model 5, which one is simpler? Which one is a simple model?
It's model
model 3 is a simple model. So in this case, therefore, for this particular experiment, I already did the experiment as a Latin square design. So I can go ahead and interpret my result as a Latin square design. But also what we need to know is then, when you do analysis, there is assumption that you make about the behavior of the model. So in choosing the model here, we are not going to just use the residue only, but we are also going to see what is the assumption of each model. Does this model actually meet the required assumption? So the issue that needs to be taken clear is that data is supposed to come from an experiment that's already designed. So you don't start getting the design from the data. You first design the study, and then the design study will give you the data, not the other way around. Here I was just trying to illustrate that. I'm trying to illustrate the effect of blocking onto the error term. If you don't block, what will happen? If I don't block, that means the error term will be bigger. That means I will have more noise in my experiment. If you block wrongly, you may also end up with having more noise in the experiment. I'm going to explain why model 4 is worse than model number 3. That one I'm going to explain is going to be related to how we calculate the variance, the final value that we have. I'm going to explain that. Is that clear?
Yes, Doctor.
Yes.
Excuse me,
Okay.
doctor.
So, yes.
An inquiry.
Yes, please.
So when you carry out an experiment, it's always good to analyze using all the models. And then when you're going to do that experiment later, you follow on the results that you have gotten and which model works best.
Well, at the end of you see now, once you design your experiment, you design your experiment with some kind of assumption in mind. So you're going to analyze your data, and if you're still going to do experiment, you learn from each previous step, no? So if I said, oh, I'm actually, because let's say these milkmen are the ones you employ on your farm, or this could be the technicians you have in your lab. So if you realize that the technicians, actually there's no difference between the technicians, so then I don't need to worry about which technician will be in my mod in the experiment. So I can use all the technicians who are available, because at the end of the day there will be no differences between them. Okay, but this will only come after you've done the study and after you've actually shown that, oh, I was worried for this, but it looks like this is okay. So next time I'm doing an experiment, this can help me to design my study properly. Have I made the right, is the clarification okay?
Yes, doctor.
Okay. So now I'm going to we are still going to look at the at this. After I've done this, I'm going to come and we look at the analysis itself. This one is just the analysis that the computer has done. So we're going to look at we have all heard about analysis of variance. So what we are looking at here is what we call analysis of variance. So after this, we are going to go back and now start doing some of the calculation and see how we reach this point. Somebody has a question? I will come back to explain this output here at some point. Okay, so here when we have different statistical models for the different design. So if you have done your experiment using completely randomized design, then you have your variable. This is what you measure. You're looking at the effect, the overall population. This is the effect of the treatment, and then this is the error term. So remember, this is similar to our second model. You see now you have the effect of the treatment, and then you have the error term. Of course, there is the population mean somewhere, which I skipped here. So this would be our model. This is the model that you'll use if you in the lab you use CRD, for example. This would be your model. Now if you use blocking, then this would be your model. You'll have the mean, you'll have the effect of the treatment, you'll have the effect of the block, and then you'll have the error term. This is now the experimental error that you have. And then for a Latin square, you'll have your effect of the mean, the treatment, you'll have the effect of the column, you'll have the effect of the row, you'll have this. Now, our column, in our case, the column were the cow effect, and then the column were the cow effect, or the column was, okay, so the column was the milkman effect. This is column 1, column 2. So the column is the milkman effect, the cow is the row effect, and then you have the experimental error. And we all saw that if at all this is the same, if for the same setup like what we had before, we rightfully indicated that the error term is supposed to reduce in this order. Of course, we saw that in one case we blocked, but then the block actually performed worse than when there was no blocking, and I'm going to explain that at some point in time. So once you've done your analysis, the next thing that will happen would then be we need to check whether the assumptions of what we call analysis of variance have been met or not. So the assumptions of analysis of variance are the assumption that is based on these particular values that we have there. Okay, are the models here clear?
Yes, Doctor.
If it is not clear to you, please.
Yes.
Okay, good. So in our CRD model, remember we are looking at the milk yield, which is our variable here, and then we are looking at the effect of the treatment, which is the effect of the feed, and this one here, and then we're looking at the error, which is this one here. So the mu here is included in this, but we can remove it. Now, okay, so what will happen is therefore that what we are doing here is what we call analysis of variance. So we are analyzing variation. Now, if we go back to our data, okay, let's go back and look at this. So this in the case of our first model, we see that the value that we are dealing with vary, no? So I want to ask a few questions. Are there variation between the different treatment?
Yes.
Okay. So you can see that this treatment here has a lower mean compared to this, like that. So there's variation between the different treatment. What about within the different treatment? Are there variation within the treatment?
Yes.
Okay. So you can see from here that for the data set that we have collected for this particular data set here that we have here, now we can see that each value varies. So you have this value being different from that, being different from that, being different from that. Now in statistics now, we want to analyze this variability and we say, how come this value is different from that? Now, can somebody explain for us why this value here is different from this? What do you think, why do we have these two different values here? What can explain the difference between this?
The variation in the
okay, so there is a variation in the treatment. This has this treatment A and this has treatment B. Is that all?
We are also using different milkmen.
Okay, so there's also variation in the milkmen. Okay, and then if you look at this and this there will be variation between the treatment, but there's also variation between the different cows, no? So yes. what we have here is that there is variation in the data that we have collected, and we want to explain that variation based on the design of the study that we started with. So that's why now we're saying, okay, now if we look here, for example, we can see that there is actually variation between the different treatments. There's also variation within the different treatment. Now, if we assume that the cows are the same, the milkmen are the same, then what would be the only source of variation? So here, let's assume that there's no, these ones are, and let's say there's no differences between the cows, there's no differences between the milkmen. So what are the sources of variation in this particular case? In the case of CRD, what are the sources of variation?
Difference in the feed.
Yeah, so there's a difference between the treatment, and what other source of variation is there apart from that?
There are experimental.
Yeah, also within the treatment there's variation. Okay, so from here you can see that there is differences between the treatment, but there's also differences within the treatment. Now, the differences within the treatment is what we consider as our experimental error. So here, when we come now to our model here, so here, the overall, the variation that we have in our data set, we can explain it because of the variation, because of the treatment effect, and anything else that we cannot explain. So what we want to do in this case, then we say, okay, can we get this variation here in the milk effect and decompose it into two parts? The part that is the effect of the treatment and the part that's the effect of the error or within the treatment. So this is variation between the treatment and then variation within the treatment. So the analysis, what we do here is what we call analysis of variance. So analysis of variance table will tell us the source of variation. Okay, so here we said there are two sources of variation. There's variation between the feeds, and then there's variation within the feed. Within the feed is the residual, or what we call the experimental error. So you can see from here that we have what we call the degrees of freedom, and then we have what we call the sums of squares, we have the mean sums of squares, we have the variance, the F value, and then we have the P, what we call the P value or the probability. So what this table is showing us is that we are interested in decomposing the variability that exists in milk yield, and part of this variability can be attributed to the effect of the treatment, and part of the variability can be attributed to any other variation that we cannot explain, that for issue of convenience we can call it our experimental error, or we call it our residual. Now this is where the design comes in now. Now if there is any other variation, like in this case there's the milkman, there's the cowman, then you may actually consider that no, this one part of this one is known because we designed an experiment that took care of that. So we need to break this one up into the cow effect and the milkman effect, and then the pure error that will remain. So this is our analysis of variance table, and from the analysis of variance table we have the sources of variation, we have what called the degrees of freedom, and then we have the sums of squares. Now, and so how many people know how to calculate the sums of squares?
I don't know how to do so.
You don't know?
I know.
Okay, you know. So who can explain? Can you explain to us how how it is done? Can you explain to us how it is done?
I think we should be knowing the total mean. After getting the total mean, and then we subtract it from the errors.
Okay. Okay. I'm going to get to that at some point. Okay. So what we want is that this is supposed to be to tell us how much variation is due to the feed and how much variation is due to the residual. So from here you can see that if you look at the 155.89 is due to feed and 140 is due to the residual. Now the next line is the mean sums of square. The mean sums of square mean you are dividing this sums of square by the degrees of freedom. So this is actually the actual variance. So remember, in our first model we had the value of 7.038. So we are going to see how this is calculated. Now after this is done, the next line here is to get what we call the ratio. So the ratio here is going to be this divided by that, but I'm not going to go into that. I'm going to Okay, so here what I'm trying to do is that let's just look only at this third column here. So this is variability due to the effect of the feed, and this is the variability due to the effect of anything else that we cannot explain. So this value 140.76 will contain the effect of the cow, will contain the effect of the milkman. Now when we go to the second model, what will happen, remember, is that we are now, the effect of the feed is not going to change. So what is going to change is that we are going to take part of this. We are going to, if we introduce cow effect, then the cow effect is going to remove part of this. If we introduce the milkman effect, then the milkman effect is going to remove part of this. If we introduce both the cow effect and the milkman effect, then they are going to remove part of this. So this value keep on reducing depending on what you're removing. So let's move to the next step. Okay, so what happens here is that after we have fitted the model, so we would have, for each value that you observe in the field, the model will give you an approximation. Now the difference between the value that you've got in the field and the approximation that the model gives you is actually the error. So here, for example, you can see that in the first data set, which is for this one here. So from this cow here, when given feed A and milk by milkman 1, we got a value of 33.8. This is the value. Then we move to 33.7 and so on and so forth. So this is the value that you pick from your experiment. Now when you come and run analysis of variance model on it, the model will also predict for you or fit for you a value. So this is the actual value. This is what the model tells you. Now the difference between the actual value and the model tells you is actually the error that the model, what the residue or the error that the model makes. So this is where any other difference that is not explained will be in this. So this is how the error, the residue is this is how the error is calculated. So for each data point there is an error term. So here you have negative 1.96, negative 1.34, and so on and so forth. So what will happen then is that once you've done your analysis, you have the actual value that you observe, and then the model also predict for you a value. According to the model, you should have got this value, but that's the actual value. So the model is a bit off by negative 1.96. In this case, the model is off by negative 1.34. In number 3, the model is a bit off more by 4 point that. So you can see, so which of this point is best predicted? Which of these 25 data point is the best, which is the model predicts it best?
Point 12.
Point?
15.
12, 15. Point 15.
Point 15. Okay, 15 is 0. So you see now the difference between the actual value and the value that the model gives you is very close. It's almost 0. Okay?
Yes.
And then which one is the worst?
Point 5.
16.
5, yeah, 5. You see the 5 is 4.76. So now this is the one that, this is now the value that we are going to study to show us whether actually the assumptions of analysis of variance is met. Question? Yes.
Why isn't it 16? Because I'm saying we are having both negative and positive values. So
yes. So in some cases, the model can over predict the value. In some cases, can under predict the value. You see, if let's assume now that I want to predict the amount of money that you have in your pocket. Okay, you have the actual value you have in your pocket. Let's say the actual value you have in your pocket is 10,000, and according to my model you have 5,000. So that means I'm underestimating what is in your pocket. But the next person could be having 10,000 and I estimate to be 15,000. So in that case, the difference will be negative while yours will be positive.
Okay.
Yeah. Okay. So now when we are looking at studying the assumptions of analysis of variance, it's actually this residue that we study, that we look at how do this residue behave. So here, for example, with the assumption here is that the first assumption of analysis of variance is that the residue, the error term here, have normal distribution with a mean of 0. And we know how a normal distribution is supposed to look like. So here we have a normal distribution with a mean of 0. So you can see from here, the center is at 0. So from here, then say, oh, the assumptions of a normal distribution is actually met with my data. So I can be happy with the results. So there are two ways of testing, looking at assumptions of normality. You can draw the histogram, or you can do what we call a QQ plot. So for a QQ plot, you need to have a line that runs at 45 degrees. And this will tell you that, oh, this data set has, so if we look at these residues, it has a normal distribution. So the residue has a normal distribution with a mean of 0. But what we could also do is we could go and plot the residue in relation to the feed that we have before. Remember our box plot for the feed. You see, this is our box plot for the feed. A for feed, B for feed. Instead of plotting this, we could actually now plot the residue for each point. So we can plot the residue for all these points, but in relation to, we look at all the residue for point A, we look at all the residue for point B. So you can see the residue for point A, the residue for point B, the residue for point C, residue for point D, residue for point E. Now, if you look through which feed has highest variability in the residue?
Feed E.
So feed E still has high variability for the residue. Now the residue in this case is the value that the model predicts, the difference between the value that the model predicts and the value that the actual value that you have there. Now let's look at for the cows. Which cow has the highest variability in the residue?
Cow 1.
Cow 1. Okay. Do you see anything strange? Do you think anything strange about the residues for the cows?
Yes.
There's a high variability between the cows.
So you can see for cow 1, all the residues are negative, no?
Oh.
Yes.
Yes.
For cow 2, all the residue seems to be negative also.
Negative, yes.
And then for cow 4 and 5, all the residue seems to be positive.
Yes.
Now, residue are supposed to be noise. So can we assume here that there's kind of a pattern here in the residual plot for the cows? So what we are looking at here is that if you look at the difference between the observed value and the expected value. So here, when the values are negative, that means the expected value is higher than the observed value. Okay. So what we are saying in this case is that for cow 1, the model seems to overestimate the amount of yield for cow 1, amount of milk for cow 1. It also seems to overestimate the amount of yield milk for cow 2, and then it underestimates the amount of milk for cow 4 and cow 5, which is not good because we don't need to see any pattern here. So from here we can actually see that the error terms seems to depend on the cow. For some cows, the error terms tend to be negative. For some cows, the error terms tend to be positive. We want it to be distributed properly. For cow 1, we want some error terms to be negative, some error terms also to be positive. The same for cow 2, cow 3, cow 4, cow 5, so that there is no pattern. So you can see from here that what this model, the CRD model is not very good because it tends to overestimate the amount of milk for other cows and tend to underestimate the amount of milk for some other cows, and that is not good. So the second assumption here is that the error terms should be randomly independently distributed, and then they're supposed to have a constant variance. So a constant variance would also say, for feed E, for example, you can see that some residuals are positive, some residuals are negative. Do we see that? Yes. And then for D, for C, and then for A, for B, we seems to see most of them being negative. But in terms of pattern, there seems to be no pattern here, but there seems to be some kind of a pattern here. Now let's look at the milkman. Okay, so we also see we have some positives and negative, positives and negative, positives and negative, positives and negative, positives and negatives. So in terms of the pattern, here we can assume that there is no pattern, here we can assume that there is no pattern, but in all cases the variability seems to depend on here on the feed. There is more variation in feed E compared to say feed B, while here we seems to have more variation in cow 4 and 5 and then cow 1, but cow 2 and 3 seems to have less variation. So here we can see that some assumptions are not met, and if the assumptions of analysis of variance are not met, that means we may not the result may actually be misleading in one way or the other. And this would also tell us that probably the model that we have chosen is not the best model. Remember, this study was done as a Latin square. So if you decide to analyze it by ignoring the cow effect and the cow and the milkman effect, you may actually end up with a model that seems not to do very well, as we can see in this case. So now let's go to the second model and see whether if we bring in the cow effect, it would change how the residual would behave. So if we bring in the cow effect, so now look here, when you look at the error term now for the cow, it looks much better now. Can you see now there are positives and negative in 1, positive and negative in 2, in 3 we seem to have more positive, and then you still have positive and negative. So compared to this model here, you can see here the pattern is a lot stronger when the cow effect is not in the model, but once we put the cow effect in the model, we seems to have everything seems to be okay. Even for the feed we seems to be okay, but we seems to have a slight problem with the milkman, with the milkman. So you can see that for milkman number 5, all the residuals are, most of the residuals are negative, and for milkman number 1 and number 2, they are all positive, but for milkman 3 and 4, we seems to have everything is okay. When we come to looking at the distribution, you see that, well, I mean, the normal distribution looks okay for this model. So we can see from here that in terms of the pattern, we seems to got a good improvement here when we put in the cow effect. Okay, so the selection of the model does not only depends on the error term per se, but also depends on the behavior of the error term. You can look at a bigger error term, but also how does the error term behave when you subject it to some analysis. Now, if we put in the milkman and we throw away the cow from the model, now can you see what's happening to the cow now? So the cow seems to be complaining that they need to be in the model. you can see cow 1 and 2 most of the values are overestimated, and then for cow 4 and 5 is underestimated. This seems to be okay, and then the residual, the milkman seems to be doing well. Okay, and then we still have this. Okay, now I just want us to go and look at a complete Latin square now. So when you go to a complete Latin square, you have the feed effect, you have the cow effect, you have the milkman effect, and then you have the error. So from here you can see that in terms of the distribution, we seem to have positive and negative for the feeds, we seem to have positive and negative for the cow, and we also seem to have positive and negative for the milkman. And then the normal distribution is okay, although slightly not better than that. So here you can see that the design seems to agree that we need to have both the cow and the milkman effect in our model, so that the error terms are randomly independent and normally distributed. But we still have the problem of the variance being constant. So this is where now you said, okay, now if the assumptions cannot be met, what can we do? And this is where you do things like transformation and so on and so forth. Okay? Any question? Any question? We are going to summarize and finish. My power has also gone off, so I'm just using a backup. Okay, so for now, we can actually now, okay, let's stop here. I don't want to start something new here. So any question?
Doctor, I just want to just get some clarification. What exactly is the purpose of the assumption of analysis of this ANOVA? Why should we have assumptions?
Yes, analysis of variance, like any tool, works based on some assumptions. If the assumptions are not met, that means the results can be unreliable. Okay? So you cannot go ahead and interpret the results confidently unless they meet the assumptions. Okay? Because analysis of variance has its own assumption that for you to do analysis of variance, the data needs to behave in a certain way, and that behavior we can look at it from the residual itself. Is that clear?
Yeah, it's clear.
Okay.
Doctor.
Any other?
Doctor,
Yes.
I would like to know how we get the degrees of freedom in the ANOVA table.
I'm going to have a. I'm going to go back and bring the calculation, how to calculate the sums of squares and degrees of freedom. This one I just wanted to first go through this, and then we can go back there and see how these values are generated.
All right.
Yeah. Any other question?
Doctor, are we meeting tomorrow?
Tomorrow we have a long department meeting. I'm not very sure. Yeah, but tentatively depends on when the meeting gets finished. I will be able to inform you by around 1.
All right, okay.
Yeah.
Doctor, I'm kindly asking that the next lecture be a physical lecture so that people can really understand this. They come with their laptops, and then maybe you can move around and help us.
Yes, we are going to run that physically. But even this one here, and what I'm going to do, when it reaches the practical part, I'm going to share with you the codes, and then we can run. Actually, when the number is not big, you can actually, online may actually be much better because I can ask you to share your screen.
Yeah.
And when you're sharing your screen, your errors can also, some people can see the mistake that you made, and the learning may actually be more effective than the physical one.
Yes, the
But
online
once you
is
have
better.
all the codes and the data, then we can follow it very easily.
Yes, yes.
Yeah, but we're also going to meet physically. After this week, we're going to have physical meeting.
All right.
Excuse me, doctor.
Thank you.
Yes.
Is it possible if you share with us some data so that when we come, we know we
I'm
can
going
use
to
it?
I'm going to do that.
All right. Okay.
No.
Yes.
Thank you.
Okay. So let's stop here.
Thank you.
Thank you too.
Thank you, doctor.